Hey guys, and welcome to your next tutorial. Sorry about the delay between all of the previous tutorials. I took on a lot more stuff than I should have in my life because I tend to do that. So that's why they've been coming out a little slow. But don't worry, I'm never going to quit making these tutorials. So even though tutorials may come out slowly every now and then, I will never stop doing them. Anyways, today's episode is spatial partitioning. I know that's something that a lot of you were really looking forward to because it's kind of a complicated concept, but it's really it's not too hard to understand. Now, what spatial partitioning is it's a way for you to improve performance of games that have lots and lots of different objects. Now, you're not going to always want to use spatial partitioning. It's not something that you should just plug into any game. It's going to make your code a little bit more complicated. It's going to be a little bit harder to manage all your objects and their positions and things like that. Not too much more complicated, but enough to where if you don't need it, you really shouldn't add it. If you've only got a few hundred objects in your scene, if your game is like that, like platformers, you're probably not going to want to do spatial partitioning. Just because it's not really going to be that beneficial to you. And in fact, spatial partitioning, depending on how you implement it, can actually hurt performance if you have way more cells than you actually do objects. But in our game that we made in the previous video, the ball game, we want to have tens of thousands of balls on the screen at one time, and all of these balls are right now constantly checking collision with every other ball every frame. And that's a quadratic blow up. We're going to get lots and lots of checks that we don't need. For instance, take this example right here. Let's say this is our window. I've drawn it as a grid right now. Normally, what would happen is in our current ball game is this red ball would have to check collision with the blue ball, even though they're not even remotely close to each other. That is a huge, huge waste of resources. If we have thousands and thousands of balls, that's terrible. So what we can do instead is spatially partition our world. And what that means, spatial basically means in space, like in this case it's going to be a 2D space. And partitioning means splitting it into parts. So what we're going to do is take our window here and separate it into these unique cells, and this is going to be a grid. So now, I don't know why it keeps doing that. It keeps. So now this red ball is in this cell, and this blue ball is in this cell up here. Now, whenever we check collision with the red ball, we're not going to just loop through every other ball in the game. Instead, we're only going to check collision with the balls in this cell right here. And what that means is we're only going to check collision with actually nothing. We're not even going to check collision. So already we've cut our computations down to 0. And up here, this blue ball is going to check collisions in this cell. And that's as simple as it is. Whenever balls move between cells, you have to make sure that you actually move them in the data structure. Basically, each cell is just going to have a list of balls that belong to it. And then whenever you want to check collision with a cell, you just loop through all the balls in that cell to do the check. Now, there's one problem with this. For instance, take a look at the top right here. This blue ball is overlapping this left cell, but I just told you it's only going to check collision in the cell that it's located in, which in this case, the position we're going to say is the middle of the ball. We're going to actually have to change our code for that because currently in our code, the position is the top left-hand corner of the ball. So to fix this issue, what we need to do is, number one, make sure our cells are always bigger than the radius of a ball. If they're not bigger than the radius of a ball, then we can have issues. In fact, they should be, they should be bigger than the radius, not the diameter. If they're not bigger, then a ball could be so big that it overlaps a bunch of different cells, and that can make this more complicated. Second thing we're going to do is whenever we check collision, we're going to check collision not only with the cell that we're in, but with the top cell, the top left cell, the left cell, and the bottom left cell. So we're going to make an L shape. So if we check collision with all of these, for instance in this case with the blue ball, we will correctly check collision with any balls in that left cell. Now you ask, why don't we check collision with all of these cells? For instance, let's say we have, I don't know, a purple ball. I'll draw me a little purple ball here. And let's say the purple ball is right here. And then we have another red ball. I really should use something other than paint for these things, but sorry. I choose to use paint, and I will continue to use paint. All right, there we go. We got a red ball and we got a purple ball. Now we want these two guys to be able to collide with each other. So you would think we would want to, whenever we're checking collision for this red ball right here, we would also want to check these cells right here. However, what's going to happen if we do that is we're going to get some redundant collision checking, meaning we're going to do multiple collision checks between two balls that we don't need to do. For instance, if we check this cell with the red ball, the red is going to check collision with the purple ball. But then, when we go and update this cell, the purple ball is now going to go left here and check collision with the red ball. So now we've done 2 collision checks when we only needed to do 1. If we always check at the top left direction, then what's going to happen is this red ball is going to ignore the purple ball for now. But whenever the purple ball updates, the purple ball is going to check all of these cells. So then the collision between the purple ball and the red ball is going to be checked. So really the hardest part about this is managing your grid data structure, because the grid needs to hold all of your objects that can collide. If you've got a bunch of different classes that can all collide together, you should probably have them all inherit from some base class, and you can just store pointers of that base class in here for collision. You're only going to be doing collision checks on the grid probably. I don't think you would really need it for anything else. So you can have a separate list for updating things like movement and all that. And let me think. I think that's all I need to tell you about this. So let's go ahead and get implementing. If I remember something while we're coding, I will mention it. Okay, now before we start implementing, there's a few things we need to do. First thing you need to do is definitely implement this new deflection calculation. My code was horribly wrong, but luckily YouTube user Sketchy502 fixed it to use proper momentum collision stuff. This is, if you're curious, this is an elastic collision between balls. You don't really need to understand how it works. Me just looking at this, I don't really know how it works. I would have to go study it a little bit. Don't worry about it. So make sure you implement that and say thanks to Sketchy502 if you see him. Wow, the mouse wheel on this mouse is terrible. And next thing we need to do is, since what we're going to be doing is making it so the center of the ball is the position instead of the top left, we need to change our code accordingly. The ball2 position.ball radius right here can just be ball2 position. Same thing with ball1. We don't need to do that offset anymore when we're doing the collision calculation. Let's see, what else? Whenever we click on a ball, we need to make sure we are doing this correctly. Let's see, is mouse on ball? We need to change that function, and that function is down here at the bottom. So here we just get rid of the ×2 for the right direction, and we need to do minus radius in the negative direction. So minus b.radius and minus b.radius. It's nice having balls that are uniform in size in the x and y direction. It makes things a lot simpler. Alright, now let's see. One more thing we need to do is when we're doing wall collision, we need to make sure that instead of checking position against 0, we need to check position against ball.radius, since the center of the ball is now the position. And then we can get rid of this ×2 here for the positive direction. Alright, I know I'm going pretty quick here, but I feel like this stuff is pretty simple, so I'm not going to spend too much time on it. And one thing we need to do is in the renderer, and I actually already did that, we need to, instead of saying ball.position x and y for a rectangle, since we are doing a rectangle, we need to subtract the radius in the x and y direction to get the rectangle to start at the top left-hand corner of the ball. Now, if I'm not mistaken, we should be good to go now. As you can see, the momentum calculation is working correctly, thanks to Sketchy. And yes, I can click on all the balls, and they're bouncing correctly off the edges and off of each other. Good. So now the center of the ball is the position. Now, we need to go ahead and implement our spatial partitioning data structure. Now, the spatial partitioning is only going to be used in position. We can still use the ball controller as normally to update wall collision and to update their movement. But we need to do a few changes here in the update balls that will handle moving between the different cells and things like that. So let's go ahead and create ourselves a new class. This is going to be our grid class. And we'll call it a class, yes. And let's call it, we'll call it spatial grid. No, let's just call it grid. We don't need to be too verbose with this. And we'll finish it, call it what you want. Now, the grid is going to have a bunch of cells, so we need to also have a cell class. I'm going to go ahead and just create it in the grid class since it kind of depends on it, or in the grid header file. We'll do class cell. And in this case, I'm going to actually make it a struct. We're going to make all of the data inside of it public. It's not going to have any methods or anything like that. So what it's going to contain is a list of balls. Now here's where you need to think for your other games about how you're going to implement this, because if you have a bunch of different objects, it might be a pain to have a bunch of different lists of all the different objects in your cell. Instead, if they all inherited from one object, then you could just have a list of that one object and use polymorphism. Now in the future we're going to be learning like my favorite thing ever, which is the entity component system that will make all of this much easier, but for now we don't know that, so we can't implement that. Sorry, I think I'm a little sick. Alright, so now we need to actually have a list of balls. So we're going to include, and we're going to say ball.h, and we also need to include vector, since we're going to use a vector for our list. You can use anything you want, but I like using a vector. And what we're going to do is say std vector, and now we could say ball, but anytime we move the vector around, we're going to have to copy all of the data in a ball. Let's see how big a ball is, because that's going to, yeah, so a ball has a lot of bytes here. That's 4 bytes, 8 bytes, plus 8 more, 8 more. That's too big. So we're going to use a pointer. That way, this is only a vector of 8 byte variables. Pointers are typically 8 bytes. All right, so here is our vector of balls, and that is pretty much all there is to a cell right now. We might change that as we go. Okay, so our grid class needs to have a number of balls, and these balls are going to be stored in cells. So what we need is a 2D grid of cells. Now we could use an array, we could use two-dimensional vector, but what I'm actually going to do is use a one-dimensional vector and treat it as a two-dimensional vector. Now the reason I'm going to do that is for cache friendliness. Whenever you're iterating through a two-dimensional vector, you're actually going to be jumping around in memory a lot more than you think, because each vector that is a row in your vector of vectors is going to be allocated somewhere else on the heap. However, if we just use one vector, like just a vector of cells, and we treat it, and this should actually be a capital C, what am I doing? And we treat it as just a two-dimensional array, even though it's one-dimensional, then we get all of the awesome cache friendliness of a array, because remember, a vector internally stores an array. And we'll call this mcells. We're going to go ahead and make this a private variable. Call it what you like. Okay, so we have a constructor and destructor. For now, I'm going to leave them there and not do anything with them. Now, we need to have a few functions. We need to have the ability to get a cell at a certain point, and we need to have the ability to get all of the balls in a cell so that we can update collision with those balls. Now, what we're going to do for getting a cell is just write a simple function. We'll write, we'll say cell. I'm going to return a reference to a cell. Get cell. And the reason I'm making it a reference is so that we can change the cell that we are getting. And we're going to get the cell at int x and int y. So we will need that. And by convention, we'll say that, I guess, y goes up. I don't know. We'll see what happens. Now we also need to, whenever we create our grid, we need to be able to specify what the dimensions of the grid are. Now what I'm going to do for that is I'm going to give it a total screen width, a total screen height, and a cell size, and then we can compute that naturally. Now we could use an init function, or we can use a constructor. This time I'm going to go ahead and use a constructor so we can get a little bit of practice with smart pointers, but you can do it however you want. So we're going to say int width, int height, int cell size. And let's go ahead and copy that into our CPP file. I hope you guys can read the text. I'm using a little bit of a smaller font size. Just to show you guys, if you go to Tools, Options, and you go to Fonts and Colors under Environment, you can change your font size. I'm going to change it to 13, make it a little bit bigger. Okay, so we have width, height, and cell size. Let's go ahead and, actually I don't even think we need to, actually we do need to store those, so we're going to say int m cell size, int m width, and int m height. You can always delete them later if we end up not needing them. So I believe I already copied it. There we go. Let's go ahead and use an initialization list like good programmers. We're going to say m width equals width, and we'll say m height is height, and m cell size is cell size. And let's tab all those over to make it nice and pretty. Now what we can do is determine the number of cells in the x and y direction. So let's go ahead and do int m num y cell, or num x cells, and int m num y cells. So that's going to be the number of cells in the x direction and the y direction. Essentially our width in cells and height in cells. You can probably come up with a better name than me. Now this is actually a really easy computation. All we got to do is say m cells num x cells equals m width divided by cell size. Now this is going to do an integer division, and it's going to actually chop off the end. So what we can do is we can make it a floating point division and then make it and round it up so that we're always certain that we're going to have the right number of cells. To illustrate the issue, if this red line right here is the width of our screen, then something like this could happen. You can see we have a border around here where we should have some cells, but we have no cells simply because we're doing an integer division and we're chopping off that extra precision. If we were to do a floating point division and then round up, then we would get an extra cell right here that would fix that problem. We could also fix it by just adding one, and we would have an extra cell, but I'd like to do the ceiling method personally, so let's do that. So I'm going to make this a float, m width divided by cell size, and then we can do the ceiling function, and this is what rounds up. And I have ceil, but you may not have it. If you need it, it may be in CMath, I believe CMath, or C Standard Library. I never know, just include them both. And we're going to do the same thing for num y cells, except instead of m width, we are going to use m height divided by, and I'll use m cell size to be consistent here. There we go. So that's going to get the number of x cells, and copy paste is the devil, the number of y cells. Now we can actually create our array with this many cells. So how do we treat a one-dimensional vector as a two-dimensional vector? Well, all we do is we basically do what C++ does internally when you make a 2D array. When you say int my array 3, 3, even though this is a two-dimensional array, internally it's actually stored as a one-dimensional array. This makes one call to new, so it's making one, well, it's not actually calling new, but it makes one allocation, so it's making one contiguous buffer. This int myArray 33 is equivalent to an int myArray 9. So what we're going to do is say mcells dot resize. Now the number of columns is m num y cells, and in each column there are x cells, or num x cells, so we're going to say num y cells times m num x cells. You will recognize this as the formula for the area of a square, because that's what we're making, or a rectangle, sorry. So allocate all the cells. And I'm going pretty slow in this video, sorry guys, maybe you can speed me up with some external program. Alright, now let's go ahead and implement the getCell function. I'm going to use fancy Visual Assist, where you can right-click, refactor, create implementation. Look at how cool that is, it made it for me. Now all we got to do is return the cell located at x and y. So first we need to do a little bit of error checking. If we'll say if x is less than 0, we're just going to go ahead and say x equals 0. We're going to go ahead and just bound it. We should probably print out an error message if that happens, but I'm not going to. And if x is greater than or equal to, let's see, m num x cells, then we're going to say x equals m num x cells. And I'm going to copy paste like an evil person and do the same for y. Let's see, thanks to Visual Assist, or actually rock margin I believe is what's highlighting all those. Num y cells, num y cells. Alright, so now we are bounding it to make sure that nothing bad happens there. And we're not going to get any array access violations, so we can go ahead and return. We're going to say mcells. And since it's a single-dimensional array, a single-dimensional vector, we have to use just one pair of square brackets. And the way we do this is we say y times m num x cells. So you can think of that as getting the area of a rectangle of height y. And then we just add m num x cells. And that will treat the 2D array as or the 1D array as a 2D array. This is a really, really useful trick. I recommend you use it all the time. In our voxel engine, we use it. It's super awesome. All right. So that gets a cell, and since it's returning a reference, it's going to return something that can be changed. It's not returning a copy, remember. So now we can make use of this grid, and we'll flesh it out a little bit more in the future. So let's go ahead and make an instance of the grid in our main game class. So let's include grid up here. Include grid.h. Oh, here we go. And let's go ahead and put it right here. I'll just put it below balls. Grid, grid, mgrid, to be more precise. Grid, let's give it a comment. Grid for spatial partitioning for collision. Awesome. And so now we have this vector of balls. Now, remember, I'm assuming that this vector of balls is never going to change. That's why I have not made these balls pointers. If your balls grid is going to change a lot, if your balls are going to get deleted and things like that, you really should probably make these pointers and allocate them with new, or just be really careful. The reason I'm doing it this way is, remember, cache friendliness. If it's not a pointer, all of these are going to be allocated contiguously in memory, and we can update their movement extremely quickly. I'm trying to go nuts on performance in this video, but you're going to need to tweak this if you make some changes. All right, so we have our grid. Actually, this isn't going to work because we overrided our default constructor in grid with int width, int height, int cell size. So we have to set those variables whenever we create our grid. Now we could do that in the constructor for main game, which we don't have one, or we could allocate it with new and do it then. Now if I was going to be a old-timey C++ programmer, I would use just a regular pointer, which I've taught you before, and allocate it with new. But thanks to C++11, we have something called unique pointer that will let us not have to worry about deleting the memory. It's a smart pointer, and I've taught you this before. To get that, you need to include memory up here at the top, so make sure you do that. And then to have a unique pointer to a grid, we say std unique pointer. It's a lot more ugly than using just a regular pointer, but it is worth it. So now this is a pointer to our grid. And we can allocate it in the main game. We'll say in init balls. Should we do it in init balls? I guess we could do it in. Actually, let's. Yeah, we'll do it in init balls. That's fine. Even though it could go somewhere else. So we'll say initialize the grid. So we can say mgrid here. What we're going to do is we're going to say mgrid equals std make unique. And the type of the unique pointer is a grid. And in parentheses here, you put the parameters that it takes. And unfortunately, the IntelliSense isn't smart enough here to tell you what you need, so you're going to have to go look. So we're going to go to grid here. We need width, height, and cell size. Oops, so width is going to be m screen width. That was weird. M screen height. And now for the size of our cells. So what I'm going to do is I'm going to use just a constant int up here. We'll say I'll put it in grid.h. No, I'll put it in main-game.h. Makes more sense here. We're going to say const int cell size, and this is going to be the size of our cells. Let's see. I'm going to go with let's look at how big our balls are, because it really depends on how big your balls are. For now, I'm just going to go with 128. I don't know. We'll tweak it. We'll tweak it as we go. At the end of the video, I'll probably pause it and find a good cell size for you guys to use. And okay, that's working. And okay, so now we just put cell size here. Size. It's always good to use constant variables rather than to just put it in here. It's much safer. Now this will make the unique pointer. Later on, if we want to delete the grid's memory manually, we don't have to. If we want to, we can say mgrid dot reset. Remember, it's a pointer. Normally you use the arrow, but when you want to operate on the pointer itself, you use dot. If we want to get a raw pointer from it, if we wanted to have something like grid star my grid equals my grid, or mgrid. Now this isn't going to work because mgrid is a unique pointer. But what we can do is we can say dot get, and that will return a raw pointer for us to use. It's not going to do any allocations or anything. It's just going to return a pointer to that internal memory. Now, if we call this twice, if we call make unique twice, there's not going to be a memory leak. What's cool about the unique pointer is it's going to, whenever it gets overwritten or anything like that, it's going to automatically delete the memory inside. And this video has turned into a unique pointer tutorial, but there you go. Now there's one thing you need to look out for when you're doing unique pointers, and that is the destruction of the unique pointers. Now we might get an error here since we don't have a destructor, but I think we might be okay since we included grid in the header file. Now if we were doing a for declaration and we weren't including grid in the header file, in order to make sure that grid gets destroyed, what we need to do is make a main game destructor, and not like that. We need to make a main game destructor, and I don't know what I'm doing here. Main game destructor, and we need to implement that in the CPP file, and we'll do that up here at the top. I really should have done this in the tutorial for unique pointers. And we need to put it in the CPP file. Now there doesn't have to actually be anything in here, but what happens is whenever your destructor gets called, wherever your destructor is getting called, that's where it frees the unique pointer whenever your class ends. So you need to make sure your destructor has include grid in its scope. Otherwise you're going to get a really weird error that is really hard to understand. As long as you have include grid.h here, or in the header file, that works as well, then this will correctly deallocate that unique pointer. Alright, so that's enough about unique pointers. We have our unique pointer, now we can use it, what is it, in init balls. So we have mgrid, and it has all the cells. Now what we need to do is have the ability to add balls to the grid, and all we're going to do is just use their position and add it after we call balls.inplaceBack here. Now here's another issue. Now our balls vector, if it's changing, any pointers to balls in that vector are going to become invalid, because as a vector resizes and changes, the internal array is going to get shifted around in memory. And it's going to make your entire grid invalid, and it's going to break everything. So keep that in mind. I am preventing that with this right here, this mballs.reserve numballs. This is going to allocate that internal vector to be the correct size. It's going to be just big enough for every single one of our balls. So when we call InPlaceBack down here, it's not going to change the size of the vector. Now if we call InPlaceBack again later, then we're in trouble, because anytime we have a pointer to one of those balls, it's going to be a mess. It's going to be bad. It's going to give us a ton of dangling pointers. So again, keep that in mind. I can't stress it enough. All right. So let's add the ability to add a ball to the grid. So we're going to say void add ball, and we're going to say actually I think the position is a float, so we'll add it as a float. Actually, we're using glm vec2, so we'll say const glm vec2 ampersand position, and then we need to add the actual ball, so we'll say ball star ball. That'll be a pointer to our ball. A dangerous pointer. I'm going to copy that and put it in here right above get cell, and it belongs to grid. So now what we need to do is get the cell that is at this location. Now we have this get cell that will get cell based on the coordinates of the cell, but we need another function. This get cell function is probably not something we're going to use a whole lot. Actually, we might. But we need to overload. I believe I've told you guys about overloading. We can overload the get cell parameter list to also take a const glm vec2 position. So let's go ahead and write a comment so we don't confuse ourselves here. Gets cell based on cell coordinates, and this is gets cell based on actual, we'll say, window coordinates. I don't know. So this one is going to get the cell based on the position of the ball. This is going to get the cell based on the position of the cell, if that makes sense. We need both of these. All right, and this belongs to grid. So how do we determine what cell we are in at a given position? Well, first we want to again do some checking here, and in this case, since we don't want to change the position here, we'll just say if position dot x is less than 0, then we're just going to return, we'll just return m cell 0. We We should do error checking here. I implore you to do error checking here, but I'm just going to return the first cell by default. If position dot x is, now we're not doing cell positions here, we're actually doing window dimensions, remember. So we're going to say m width. Then we say return cell 0 again, and I'm just going to copy this for all of them. The reason I'm using such a crappy mouse right now is because I don't have enough USB ports to plug in my keyboard and my good mouse and my headset at the same time. So I'm having to use my Logitech mouse that came with the keyboard, and it's not as good as my Death Adder. Alright, if pos_y is less than m height, there we go. So there's our very bad bounds checking, just to make sure nothing bad happens. And now what we need to do is determine what cell we're in, and we can do that with just a simple integer division. We can say int cell x equals pos.x divided by, and that is m cell size, and int cell y equals pos.y divided by m cell size. Now the compiler is going to yell at us saying that we're doing a floating point division and putting it in an integer, so we can cast this to, we don't want to cast that to an integer, that would be bad. We want to cast the result of this to an integer so the compiler doesn't tell us that we are doing something stupid, because we know what we're doing. Alright, now we have cell x, cell y. Now we can return, actually, yeah, we can just do our bounds checking in get cell. We can have get cell call get cell. That's pretty cool. So now we can call get cell again on cell x and cell y. Look at how nifty that is. 3 lines of code. Alright, so now for add ball, we need to determine what cell the ball exists in, and we just need to add the ball to the vector of that cell. So we're going to say cell ampersand, because remember, we are making a reference here. These, or cell, we'll just call it cell, equals get cell on pos. Like that. And that'll get the cell that the position belongs to. And now we need to add the, and I just realized we don't actually need the position here, since the ball contains a position. Look at that. So that's 2 mistakes I've made so far. So we'll say ball dot position, arrow position, since it's a pointer. So we get the cell there, and then we just need to add the ball to that cell. So we're going to say cell dot balls dot pushback of ball. You could also use in placeback, but I don't think it actually makes a difference if you're just pushing back an object. I don't know, I haven't benchmarked it. There we go, so that's all there is to adding a ball to our grid, really simple. Let's go into init balls, and anytime we in place back a ball, let's also add it. So we're going to say mgrid dot arrow add ball, and we're going to say the address of mballs dot back. Now dot back will get the last element in the vector, and we're getting a pointer to it. Danger, danger. Alright, add the ball to the grid. If you ever call in place back after init balls, grid will have dangling pointers. There. Now you guys can't get mad at me if you screw this up. Okay, so that adds all the balls. Now we need to actually handle the grid in our ball controller. The ball controller is also going to use the grid for all of our spatial partitioning stuff. So in update balls, we'll just pass in a pointer to the grid. So let's go ahead and include grid up here. Actually, let's be fancy and use a for declaration. We'll say class grid. Remember, the point of for declarations is to improve your compile times, because if you include grid.h up here, then every file that includes ballcontroller.h also has to include grid.h, even if they don't need that implementation. Okay, so we're going to pass in the balls, and we're going to pass in a grid pointer. Now you can only do a for declaration if it's a pointer or a smart pointer or a reference. If it was just a grid, mgrid, that wouldn't work, but obviously we don't want to do that. So grid, so that's going to happen on update balls. And that's probably the only thing. We'll probably need to pass it in for check collision. Yeah, definitely. So let's pass that in. So I'm going to copy this, check collision here. Alright, so let's go into ball controller and add that in, grid, and check collision is down here. Grid, ball 1, ball 2. Now, when we're doing movement, we need to be able to move the ball's position to different grid spots. So we need to check anytime it moves, did it go to a new position or a new grid location? And we're going to need to do that after movement, and we're also going to need to do that after collision, because collision can also change the position of our balls. So to do that, what we need to do is, let's go to grid.h. All we need is get cell here. But what we also need to do is have each ball keep track of what cell it belongs to, so that it can remember what cell it was in the previous frame. So let's go ahead and do that here. And since it's plain old data here, we can just use a for declaration. There's no functions that use it or anything like that. We're going to say class, well, the constructor will use it, but it won't do anything with it. Class grid, no, class cell, sorry. And we're going to say cell star owner cell. And like good programmers, we're going to initialize it to null pointer, because null access violations are a lot easier to debug than random memory access violations. And whenever we construct the ball, we're not going to do anything with owner cell, but whenever we add the ball in, in grid, we're going to go ahead and set the ball's owner cell to that cell. So we'll say ball dot owner cell equals, and now here's an issue. If we say the address of cell, if I'm not mistaken, that's actually going to be the address of our local variable, our local reference, but I could be wrong. I'm pretty sure that's the case.